Hello and good afternoon, friends. Welcome to the CEC EduSet live lecture. Dear friends, as you know that we bring for you different topics under environmental sciences, and we talk on different topics, various issues. Some issues are of great concern, and through these issues, we want to create awareness, and sometimes we give you immediate and very good information with the help of which you try to understand your environment. Dear friends, in this session today we are going to talk on atmospheric radiation. We are going to discuss what basically atmospheric radiation is, how it is caused, and for this we have again with us in our studios Dr. Arun Kumar Srivastav. Dr. Srivastav is Assistant Professor in School of Life Sciences, Jawaharlal Nehru University. So dear friends, let's have a look on the idea of atmospheric radiation. Let's try to understand this topic with the help of our expert Dr. Arun Kumar Srivastav. Dr. Srivastav, welcome to the EduSet lecture.
Thank you, Geetka. Good afternoon, everyone. Today we will discuss on a very important topic, that is atmospheric radiation. We have heard about atmosphere, we have heard about radiation, and I think many of you would have also heard about atmospheric radiation. But atmospheric radiation is a very vast field, and it is not a very small or topics which can easily be covered or one can understand in a very short span of time. As far as atmospheric radiation are concerned, atmospheric radiation is the thing by which the life on earth is possible, and life on earth sustains, life on earth flourishes. If there is no radiation, the life won't have been possible on earth. Now the question is, what is the origin of this atmospheric radiation? In fact, there are many sources of atmospheric radiation, but the major source by which our atmosphere has the radiation, and in fact those radiations, the atmospheric radiations which causes many atmospheric phenomena, whether it is wind, blowing of wind from one place to the other, different forms of winds like tornadoes, typhoons, etc., etc. Apart from winds, the other atmospheric parameters are atmospheric phenomena which are basically caused somehow by the atmospheric radiation or rain. If there wouldn't have been radiation, there wouldn't have been any possibility of rain, and if there wouldn't have been rain, there wouldn't have been life on the earth. Apart from that, humidity, pressure, etc., etc., all these things are basically caused or basically originated by the atmospheric radiation. So now the question is, what is atmospheric radiation actually? Now, as far as the atmospheric radiations are concerned, the major source of atmospheric radiation is the sun. Sun, which is the main source, or we can say it is possibly the only source for the atmospheric radiation. Apart from that, the sun transfers energy through the earth by radiating electromagnetic waves. In vacuum, electromagnetic waves travel at a speed of light, that is 3 lakh kilometer per second, or sometimes we also say 3 into 10 to the power 8 meters per second. The continuous electromagnetic spectra distinguishes different types of waves based on wavelength and frequency. Now, coming back to the atmospheric radiation is mainly caused by the sun, which is a major source of electromagnetic waves. This electromagnetic wave is comprised of many different forms of waves. Different forms of waves, I mean the waves with different frequencies and different wavelengths. However, it is not all the frequencies or wavelengths reaches to the earth, but there are some frequencies and wavelength which reaches to the earth. Now the question is, what exactly the electromagnetic wave is? We all have heard that electromagnetic waves are basically a type of wave having two different components of electrical nature as well as the magnetic nature. These two different natures, two different types of component of electromagnetic waves propagate, they are perpendicular to each other, and they both are perpendicular to the direction of the propagation of wave. Now, coming back to the atmospheric radiation, the earth basically receives 1,74,000 terawatts of incoming solar radiation. This is also known as insolation at the upper part of the atmosphere. Approximately 30% is reflected back to the space, while the rest is absorbed by clouds, ocean and land masses. The spectrum of solar light at the Earth's surface is mostly spread across the visible and near infrared ranges, with a small part in the near ultraviolet range. Most people around the world live in the area with insolation levels of 150 to 300 watts per square meter, or 3.5 to 7.0 kilowatt hour per meter square per day. So, this is the amount of solar radiation that most of the people receives every day. Now, here in this picture, the electromagnetic waves illustration is given, how the electromagnetic waves looks. Here we can see there is a source from where the electromagnetic wave is propagating or coming out. This is coming in one particular direction, and it has two different components. One is magnetic field, another is electrical field. These two are perpendicular to each other, and they themselves are perpendicular to the direction of the waves propagation. However, this is not the topic of our discussion. I just wanted to let you know what is the nature of the solar radiation or the radiation of Earth which we have. Now, how the heat is transported in the atmosphere. Transport of heat is accomplished by the conduction, convection and radiation. In fact, there are three different methods by which the heat which is in the atmosphere is transported or transferred from one place to the other. I told you the major source of the atmospheric radiation is sun. So, once the sun's radiation reaches the earth, or when it penetrates into the atmosphere of the earth, afterwards its major aim is how to propagate from the upper part of the atmosphere to the surface of the earth, and from one place on the earth to the other places of the earth. Here it is pertinent to mention that here it is important to mention that most of the radiation which is coming on the earth's surface is from the solar radiation. And one more important thing I would like to mention here, that the earth or the atmosphere, what I mean here is basically the combination of both, I mean earth as well as the atmosphere. Atmosphere means the layer or the portion of the atmosphere from the earth's surface to approximately some 100 or 200 kilometers from the earth's surface. So, entire these two things, that is atmosphere as well as the earth's surface, together makes the atmosphere of the earth. Now, once the radiation strikes at the top of the atmosphere, the next aim is of this radiation is to be transported from the top of the atmosphere to the earth's surface, and once it is received at the earth's surface, then the next thing is how it is transported or transferred from one place on the earth to the other place. So, there are three different methods how this radiation is transferred. It is conduction, convection and radiation. What is conduction actually? Conduction is basically a method by which the kinetic energy is, or the radiation is transferred by the molecular collision. I mean, what happens when the radiation strikes on the top, on the surface or some portion of any material, then that particular molecule where it has struck exactly struck is kinetically energized, and that energy is transferred to the next or adjacent molecule, and that molecule transfer it to the next one and to the next one, and this is how the heat is transferred from one portion to the other. The example is, if we heat a rod, suppose we have a rod of 1 meter, and if we put one portion or one end of that rod in the flame, after some times we start feeling heat, although that portion or that part or that end is far off from the flame. So, how it is transferred? Here the conduction method is working. So, what has happened actually, the end which is in the flame or in directly contact with the flame has been heated up, and that heat is basically is transferred to the molecule, and that particular molecule has transferred that heat to the adjacent or next molecule, and the next to the next, and then next, and this is how the heat from one end has been transferred to the other end. The same thing is happening in the case of atmosphere. This how the radiation is transferred by conduction. Here we are not having any rod or any material thing, solid thing, what example I have given, but we have the material which is basically air. So, in air what happens at the top when the radiation is struck, that radiation transfer its energy to the molecule at the top and then to the next, and this is how the heat has finally been transferred from the top of the atmosphere to the lower part or the surface of the earth. The next one is convection. How the convection works actually. Convection in this method, basically heat is transported or transferred within a fluid by bulk motion of the fluid itself. The best example is how water is heated. Suppose we have water and the water is kept on the flame. So, first the bottom portion of the water is heated, and that molecule or those portion goes to the upper part, and upper part which has comparatively colder water will come to the bottom, and a circulatory motion is started, and this is how the entire water is heated. This is known as convection. The same thing happens in the atmosphere. Once the atmosphere at the top has been heated, and then that hot air transferred to the other place, and when it creates an empty space that is filled by cold air, and this is how a circulatory motion takes place and the heat is transported from one place to the other. This is the method convection. So, there we have discussed two methods, conduction and convection. The third one is radiation. Radiation is a method by which energy or the heat is transferred, and it takes place in a vacuum. For this there is no need of medium like what we have discussed or what we have taken example of rod and water. Here the case of air, in the case of atmospheric radiation we took, but in radiation there is no need of any medium. The heat is transferred from one place to the other without the help of any medium. So, in vacuum this is the only method by which the heat is transferred, because you people might be having a question in your mind that sun is far off from the earth atmosphere system. So, how, and the most of the distances sun's radiation which travels in is in the vacuum. So, how the heat is transferred from the sun to the top of the atmosphere is by the method radiation. Now, there is one thing which is pertinent to mention here, that conduction and convection, that method of heat transport by conduction and convection is also called as sensible heating. Sensible heating means we have involved a medium, there is a medium by which the heat is transferred. The other meaning of the sensible heating, which is also of very importance, is that in case of sensible heating, although the molecules are energized, molecules are heated up, it first receives energy, then it transfers from itself to the other molecule, to the third, then fourth, then etc., but it is important to mention here that bulk does not change. So, in case of sensible heating, which is by conduction and convection, although the heat is transferred, but there is no change in pressure and volume. So, one important thing one should note here, that the most of the heats in the earth's atmosphere system is transported by radiation and convection and conduction, but the bulk does not change. There is no change of pressure as well as the volume of the medium with the help of which this conduction and convection takes place. Now, about the solar insolation, what I have already discussed, the solar insolation, I have given some information about the solar insolation. Here I would like to mention in details The solar insolation is the amount of solar radiation received at the Earth's surface. I mean the amount of heat which is received by the surface of the Earth at any point of time at any specific place is called as solar insolation. And since we all know, although Earth rotates around its own axis, simultaneously it also revolves around the Sun. So, there are two motions, one is rotational motion of the Earth around its axis as well as the revolution motion which is around the Sun. This revolution motion is in elliptical orbit. So, the Sun is not exactly at the center, but Sun is at one of the foci of that elliptical orbit. So, the distance between Earth and Sun is not continuous, but changes over the time or from time to time. Here it is important to mention that Sun is closest to the Earth in the month of January, precisely that is 3rd January, and this event is called as perihelion. Perihelion is, it actually implies that the distance between Sun and Earth is shortest, and the distance is basically at that point of time is 147 million kilometer. The Sun is farthest from the Earth on 4th July, that is also called as aphelion, and the distance between Earth and Sun on 4th July is 152 million kilometer. One would be surprised that January is the month of winter. I mean it is cold, while here it is given that the Sun is closest to the Earth. How it is possible? But it should be actually hotter period, but it is not the case, because Earth, which is simultaneously rotating around its own axis, is not exactly vertical, but tilted at some angle, that is approximately 23 degree. So, what happens, this tiltation actually is responsible for the cold in January and hotter period in July. So, Earth is basically tilted at an angle of 23.5 degree. As the Earth revolves about the Sun, it is tilted on its axis by an angle of 23.5 degree. The Earth axis always points to the same area in space if we view it from the distance star. I mean it is constant at one direction. So, what happens when it is revolving around the Sun? So, what will happen, sometimes that axis or that particular face will be towards the Sun, but when it goes exactly opposite of that, that face or that portion will become away from the Sun, and the lower portion, or we can say the southern portion of Earth, will become nearer to the Earth. This is why when there is a summer in the southern pole or southern hemisphere, then there is a winter in the northern hemisphere. The Earth's axis, thus in June, when the northern hemisphere is tipped towards the Sun, more direct sunlight and long hours of daylight cause warmer weather than in December, when the northern hemisphere is tipped away from the Sun. I think this can be further more clear with the help of this picture. There are different 4 locations of the Earth are given here. We can see here in the month of December, when the Sun, although the distance between Sun and Earth is more or less closer, but the northern hemisphere or the top of the northern hemisphere is away from the Sun. So, there is a winter, but if we see the southern portion or the southern tip of the tip of the southern hemisphere is facing to the Sun. So, there is a summer. If we see here in on the March 20, although it is not far, not very close. So, the weather is more or less pleasant, but in the month of June, the tip of the northern hemisphere is facing the Sun. So, it is hotter period, or we can say we are receiving more radiation, and similarly we can say that in the month of December we are receiving comparatively lesser radiation, whilst in the month of September and in the month of March we are receiving average radiation. The December's period is known as winter solstice, while the March 20th period when we receive the average solar radiation is known as vernal equinox. Similarly, June 21st period when we receive a maximum amount of radiation is called as summer solstice, and September 22 period when we receive again the average amount of solar radiation is called as autumnal equinox. The next, how the solar radiation varies from, so far in the previous picture actually we discussed the total global radiation. We had some idea about the total global radiation. Now the solar radiation is again not constant from one place to other place on the even on the earth's surface. It varies from one latitude or from one place to the other. So there is a significant and very important variation of solar radiation or the atmospheric radiation on the latitude as well. Now here in this picture it can be clear how the solar atmospheric radiation might vary from one latitude to the other. If we go to the higher latitudinal portion, or if we reach towards the if we reach towards the polar side, we will see the earth does not actually the beam of solar radiation does not actually finds a plane surface or a total perpendicular surface, otherwise it would have exactly been reflected back or completely been reflected back, but it finds a tilted or slanted surface. So instead of being completely reflected back towards the direction from where it is coming, it is getting reflected into some other direction, but it is not reflecting being reflected with a size of the beam, but in a widened size. So we can say here it is putting a larger footprint because it is covering the same amount of beam is covering a more surface area and getting reflected or refracted. But as far as the equatorial portions are concerned, which is at the bottom, you can see the solar radiation how much it is striking, it is coming back because it is finding here a completely perpendicular surface. So here the footprint is smaller, and in the previous case we can say the footprint is larger because it has covered a larger area. And in the second case we can say there is a weak reflection. In both the cases the input were almost same, and in this in the first case or towards the polar side we can say the reflection is stronger. I mean a good amount of solar radiation has been reflected back because it has covered a good amount of surface area. Now what happens, the annual heat balance of the earth atmosphere system as far as if we take into account the latitudinal variation. Already we have seen that there is a strong reflection in the polar region, but there is a weak reflection in the equatorial region. So we can say that equatorial region are obviously hotter than that of polar region. Here it is clear that in this picture at the right hand side you can see there are two lines, one is continuous line, another is dotted line. The continuous line represents the incoming sunlight whilst the dotted line represents the outgoing heat. Here we can see, and along the x axis at the top of the second right hand picture, the heat received at the earth's surface, it is given in calories per square centimeter per minute. Now we can see here at the higher latitudes, especially beyond 40 in both the hemispheres, southern as well as in the northern hemispheres, we will see the heat or the incoming solar radiations are lower whilst the heat lost is higher. So, finally, we can say that in these two areas, I mean the areas beyond the latitude 40 degree or 40 to up to 90 degree, we can say there is a average annual heat lost, but whilst in the equatorial region, or that is we can say in both the hemispheres from 40 degree to 40 degree, from 40 degree north to 40 degree south, we will see here that incoming sunlight or incoming solar radiation is more than that of outgoing heat, because again this is happening because of the weak reflection that we have discussed in the previous slide. So, here we will see that in the equatorial region, which is between 40 degree to north to 40 degree south, is there is finally a heat gain, while in both the hemisphere beyond 40 degree, I mean in the northern as well as in the southern hemisphere, there is a final heat loss, but those two heat loss compensates the heat gained in the equatorial region. So, finally, there is a heat, I mean heat is completely balanced, although somewhere it is lost, I mean somewhere it is in negative and somewhere it is in positive. And this is why this is also one of the major reasons why the equatorial regions are hotter while the polar regions are colder. The next, this heat imbalance basically creates the different winds pattern. What happens when there is a heat difference or there is a gap in heat? This will create the differences in pressure, and that pressure will give rise to the blowing of wind or the atmospheric motion. We can see here in this particular picture, which is also titled as general circulation model. We will see here that what happens because of that heat imbalance, there is a severe low pressure at the equatorial region. Why this low pressure area? Because there is a surplus heat, and that surplus heat, what happens, because that air is very hot in comparison to polar regions. So, the air will start rising up and up. So, because of that rise in air, there will be a creation of low pressure area at the surface, and this is why this entire equatorial region with a low pressure area is also known as doldrums. And if we go little higher, that is approximately to up to 30 degrees, which is comparatively colder. I mean this is the area where there is a annual heat loss, not exactly loss, but comparatively it is lost in comparison to the equatorial region. So, we will say because of that there is relatively high pressure region, and because of that high pressure region to fill, because there is a gap, I mean at equator we have low pressure region, and while at 30 degree north as well as at 30 degree south we have comparatively high pressure region. So, to compensate that high pressure and low pressure region, what will happen, that atmosphere will start moving or atmospheric motion will start taking place, so that the pressure gap can be filled, and to fill that pressure gap winds start blowing, and the portion of that 30 degree northern hemisphere and 30 degree southern hemisphere is known as horse latitude, because it is a place which is full of wind blow. I mean here there is a significant wind blow, and because of that wind blow, why this wind blow takes place? Because the pressure has to be compensated from 30 degree north south to the equatorial regions. And if we go further up towards the polar side, which is around 60 degree, what we will see that again there is comparatively a high low pressure area, which is known as polar front. It is again a very cold portion. The same thing is in the northern hemisphere as well as in the southern hemisphere. And this here in this picture, because of these pressure differences, we have got different wind patterns or wind blowing patterns, and these have also been given by different names. I mean, those wind patterns, at the top, the wind pattern which is at the top is called as polar cell, while which is between 30 degree north, 30 degree to 60 degree in northern hemisphere as well as in southern hemisphere is known as Farrell cell, whilst which is between equator and 30 degree north and 30 degree southern hemisphere is called as Hadley cell. And these are different wind patterns, and they are named because of their nature is different as far as their direction as well as their average wind velocity is concerned. Now, the basic concepts about the atmospheric radiation. The subject of atmospheric radiation is of concern with the transfer of energy within the atmosphere by photons or by electromagnetic waves. The relevant photon fall into two classes. One is solar photon, which is also called as short wave, and the wavelength is between 0.1 to 4 micron, and the other one is thermal photon, which is also called as long wave, and the wavelength of this particular long wave is between 4 to 100 micrometer. Now, what is the difference between this short wave as well as the long wave? The short wave or the solar photon are the radiations which are actually coming from the sun. So, what happens actually, the radiation comes from the sun and it is absorbed by the earth. So, what happens in the entire solar light duration, earth keeps on absorbing, some portion is reflected back, undoubtedly we will discuss it, that is approximately 30%, but most of the remaining are absorbed by the earth. And afterwards what happens, earth, it is not that earth will keep on absorbing, but it re-emits back. But when it re-emits back, its nature changes. I mean, although it came in the form of short wave radiation means waves having wavelength shorter. Here in this particular case, the wavelength range is between 0.1 to 0.4 micron. But what happens after absorbing, earth starts re-emitting back, and when it re-emits back, its nature is completely changed. Initially it was short wave, but now it has been changed to longer wave radiation, and in this particular case its wavelength has now been changed from now the wavelength has been changed to 4 to 100 micron, and thereby changing the significant characteristic of that particular, because there is a significant difference as far as the characteristic or energy carrying capacities are concerned for short wave as well as for the longer wave radiation. Further elaborating it, the solar photon or the short wave radiations which come from the sun are not of one nature. I mean, they can broadly be subdivided into three different categories, that is ultraviolet, visible and infrared rays. Ultraviolet's contribution among the three is lowest, and that is 6.4%, whilst the visible's contribution is maximum, and this is 48%. Infrared contribution is second to the visible, and that is 45.6%. Altogether is 100%, and the wavelength of the ultraviolet is below 0.38. I mean, I told you it is from 0.1. So, we can say that the wavelength of the ultraviolet rays will be somewhere between 0.1 to 0.38, whilst the wavelength of visible radiation will be 0.38 to 0.78 micron, whilst that of the infrared the wavelength will be beyond 0.78, or we can say 0.7824 micron. So, we have three different type of waves or radiations which are received by earth from sun, and they are ultraviolet, visible, infrared. The maximum is visible, the second one is infrared, and the lowest is by ultraviolet. Whilst earth, when earth re-emits back, it re-emits in only one range, and that is in infrared region, which is 4 to 100 micron or 100 micrometer. The radiation which is emitted by earth is also called as terrestrial radiation. So, we have solar radiation as well as the terrestrial radiation. This terrestrial radiation is also important. It also governs and decides many atmospheric phenomena. We will discuss it later on. So, atmospheric radiations have to be governed by different rules, because in physics perhaps we have studied different radiations rules, and in fact those different radiations rules will be employed as far as our Earth's atmosphere system is concerned. The first one is Planck's law. Planck's law is fully employed here in Earth's atmosphere system. Planck's law is basically for a black body radiation. It is also called as theory of black body radiation. What is a black body? It is basically a theoretical construct, and it can be defined as a body that completely absorbs all the radiations which fall upon it. So, what is a black body? I mean, it is a kind of body, it does not reflect or refract or scatter any radiation which falls upon it, but it absorbs all the radiations. In our case, I mean the sun, atmosphere, earth system, sun and atmosphere, earth system, although our our earth atmosphere system is not a perfect black body, but for many reasons and many to completely address many phenomenon, we consider it as black body, because once we consider it as black body, many laws can be usefully applied and many problems can usefully nicely be solved. So, our Earth's atmosphere system can to some extent be considered as the black body radiation. Now, the next law is Planck's law. As far as this definition is concerned, Planck's law can be described as the electromagnetic radiation emitted by a black body in thermal equilibrium at a definite temperature. Here in this picture we see how the Planck's law is described or illustrated nicely. Here we have spectral irradiance along the y axis and wavelength along the x axis. Now we will see that when if we have any very hot body, very hot body, and what happens, it actually emits, or the wavelength which is coming out of that body is basically peaked in the visible range. I mean, most of the wavelength that it emits is in the visible range. As soon as its temperature starts decreasing, the peakedness of the visible range keeps on decreasing. I mean, it becomes little flatty than that of the hotter body, and if it further decreases, it does not actually peaks in the visible as well as the UV range. Now, in this picture we can see there are three different lines, blue, green and red. The line which is in blue is basically it basically represents a body which is very very hot, and that is at a temperature of 5000 Kelvin. So, it is peaking, or it gives a peak in the wavelength range of 5 in the visible range, while the next hot body is at 4000 degree Kelvin, and although it has a peak, but that peak is shifting from visible range towards the infrared range. I mean, it is not sharply in the exactly in the visible range. So, and if we further decrease the temperature, if we lower it to 3000 degree Kelvin, and we will see here the peak has more or less gone. I mean, it does not peak in the visible range. Now, what is Stephen Boltzmann law? It is also important because the Stephen Boltzmann law can again address many of the atmospheric phenomena, many of the radiation patterns of Earth atmosphere system. What is Stephen Boltzmann law? Basically, it is the rate at which object radiates heat, the rate at which object radiates heat is proportional to the fourth power of its temperature. It can be given as the intensity of radiation what is coming out of any hotter body is equal to constant into the temperature of that particular body to the power 4. Thus, the intensity of radiation which is emitted from the solar photosphere or from the sun which is at a temperature of 5008 degrees centigrades, while the earth's temperature, earth is also radiating some heat because it is also hot, but its temperature, average temperature is 15 degrees centigrade. So, there is a huge difference. So, we can say the intensity of radiation which is coming from the sun and the intensity of radiation which is coming from the earth, there is a difference of 1,60,000 times. I mean, we can see it from this formula. There is a division of 5800 to 288 to the power 4, and finally, it gives a value of, it is in fact more than that, a value of 1,60,000. So, the intensity of solar radiation which is from the sun is 1,60,000 more times more than that of the radiation which is coming out of the earth. The third one is Wien's law. We can define Wien's law as a temperature, because we can describe the Wien's law as temperature of an object increases, the wavelength of most intense radiation emitted decreases. We will elaborate it further. Wavelength of maximum intensity in microns is equal to 3000 upon T. Wavelength is in microns, wavelength in microns a millionth of a meter. Micron is basically a millionth of a meter, and temperature is in degree Kelvin. For example, a heated piece of iron, when we heat a piece of iron and when it starts glowing, first its color which appears is in red, and if we further enhance the temperature, later on it becomes orange. If we increase the temperature further and further, it eventually becomes white. So, initially it was red, then it became orange, and later on it became white. The wavelength of the red is maximum, while it is comparatively lesser of the orange, and even it is lowest in case of white. So, what is happening actually? If we increasing the temperature, the wavelength which it is emitting is keeping on decreasing and decreasing. So, with the lower temperature, the radiation or the visible radiation which we will get will be at higher wavelength, and as we start increasing, the wavelength will start decreasing. So, I think today I think in the next class we will cover the remaining portion. First we will continue with this different radiation laws like Planck law, Wien's law and Stephen Boltzmann law. Later on we will apply those radiation methods to understand the various atmospheric phenomenon, especially the atmospheric circulation, motion, etc. So, with this we end today's lecture on atmospheric radiation.
With this note, thank you, sir. Thank you once again for giving us a precious session and giving us in-depth knowledge on this very topic, that is atmospheric radiation, though we have some few minutes left. So my question to you is, if we are talking about atmospheric radiation, does the atmospheric radiation is the part of the atmosphere which persists globally, or it has some areas or regions also?
Naturally, in fact, it covers the entire Earth or our global system, but it is not constant. Everywhere the atmospheric radiation varies in space as well as in time. So what I mean to say is that the atmospheric radiation is different at equator. If we go towards the pole or towards the upper part of the globe, it naturally keeps on decreasing. And apart from that, if the atmospheric radiation is something at equator or at this place, this will vary from time to time. This may become different in December, it will be different in March, it will be different in June, it will be different in September, again it will be different in December. So in space and time, this atmospheric radiation is highly variable.
Thus, we can say that it keeps on varying from a place to place within the globe, also within the, if we talk about the Earth also. So, if the atmospheric radiation, or if we say that the radiation in the atmosphere increases, does it has ill effects on the environment?
Naturally, because of the, as far as atmospheric radiation is concerned, because of, we have heard of this greenhouse effect, because of various anthropogenic activities, the heat which is coming, the heat comes and certain amount of, the similar amount of heat goes back. So the constancy is maintained. So, but because of the greenhouse effect and different anthropogenic activities, the heat which is coming and the heat amount which exactly should go back, there is an imbalance. That amount of heat is not going back. So, and some portion of that is kept on trapping, and it is happening every day. So one day, although it is very, very small, so one day some amount is remained or retained here, tomorrow again that again a small amount is retained, day after tomorrow again that is a small amount is retained. So finally what will happen, this will imbalance the heat balance, and which is finally resulting of what is very much popular, or which is of very much concern, that so-called global warming. So the global warming is because of the retainment of solar radiation, which actually shouldn't have been, and this retainment is happening or is taking place because of various polluting regions or various type of pollutions.
Definitely, this is the reason which Dr. Arun Srivastava has explained to us, that how the radiations are caused. Now, sir, the question arises, as we know that our atmosphere has various levels, and each level is defined by different names like troposphere, stratosphere. So, atmospheric radiations exist in particular strata, particular
in fact,
level.
I told you that this atmospheric radiation doesn't mean the radiation of the Earth. This actually means the total system, and this system actually involves the Earth, including ocean, etc., as well as the atmosphere, and that atmosphere basically which includes different layers. So this Earth system is the combination of Earth as well as the different portions of the atmosphere, and that solar radiation plays a very important role in various atmospheric phenomena or different layers of the atmosphere as well as upon the Earth's surface.
So this is all what Dr. Arun Kumar Srivastava has explained to us on our topic, that is atmospheric radiation. Dear friends, I would like to tell you all that Dr. Arun Kumar Srivastava would be visiting us tomorrow again, and we would be discussing more on the atmospheric radiation. Till then, we would like to tell you all that if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in, and very soon we are going to upload this lecture on YouTube so that you can study what Dr. Arun Kumar Srivastava has delivered with the help of this EduSet platform. So till then, take care, goodbye. Thank you, sir. Thank you so very much.